A motor is turning a pinion gear with a radius of 1 centimeter, and it applies a torque of 20 Newton centimeters to that pinion gear, and it's rotating 100 RPM. It drives a gear with a radius of 3.0 centimeters, and we want to know. So let's sketch the two gears. So here's the pinion gear, and it's got a radius like that, and then we'll say, okay, this one's got 3 times the radius, so 1, 2, 3. So there's my radius, and I'll try and draw this as best I can to the right ratio. And don't even ask me to draw the teeth on this thing. I'm going to call this gear A and this gear B, but this is the one that's driven. And so let's say it's spinning like this. Now we want to know what force does the driving gear apply to the driven gear. So here's what we know. We know that the torque on gear A, this was given. The torque on gear A was 20 Newton centimeters. And we also know that the torque is the force times the lever arm. I'm going to use the physics equation for it because a lot of you are going to be taking physics or AP physics. So this is R times F, the radius times the force. The order doesn't matter for this class. It will matter in when you get to AP Physics because you want to go R times F. Believe it or not, because it's the cross products and stuff like that we're not going to worry about in here. So we know what R is, and we want to know what force is gear A, and this is part A. What force is gear A going to apply to gear B? Well, if this is how much torque you have, and here's your radius, just divide by the radius on both sides to get your force. So the force is going to be equal to the torque, which is 20 Newton centimeters, divided by the radius of gear A, which is 1 centimeter. And if you'll notice, I always show my units with my calculations so that if I'm using centimeters and meters and millimeters or inches or whatever, I don't accidentally mix units that aren't appropriate for each other. But in this case, they are appropriate. The centimeters cancels out, and you end up with a very simple answer. The force that gear A applies is 20 newtons. 20 newtons of force. Now, here's the way it works. Because of Newton's third law, this torque goes around like this. A applies to be a force like this of 20 newtons. Now, by the way, this is the force on gear B. Is in that orientation. But look, please listen right now. This will really help you in physics too when you take it. For every force on one object, there is an equal and opposite force on another object. That is a law of nature. There is never an exception to that. So the fact that we have this much force on gear B means that we have an equal and opposite force on gear A. Now, but you say, but wait a minute, doesn't that apply? Like here, the motor is applying a torque like this. But isn't this the force that B applies to A, applying a torque in the opposite direction? And the answer is yes. Yes. Because one of the things that's implied in this problem is those gears are turning at a constant rate. So this torque, so if it's turning at a constant rate, that means there's no net torque on gear A. If there's no net torque on gear A, it's not going to angularly accelerate. It's just moving with constant RPM, constant angular velocity. So it's totally okay. In fact, it has to be. So this is the force on gear A. And so this is an application of Newton's third law. For every force on one object, gear B, there is an equal and opposite force on another object. Okay, now, let's figure out for part B. Oh, this was B, I'm sorry. This was A, and this was B. Now for part C, it says, what torque is applied to the driven gear? Well, here's the driven gear. And what's the other vocabulary for driven gear?
Pinion.
Well, no,
the driven, I'm sorry.
The what?
The spur.
The spur. So this is the pinion gear. This is the driving gear. This is the driven gear. So that's called the pinion, and this is called the spur. Mm-hmm. Okay, all right. So now the torque on gear B is equal to, well, it's going to be equal to R times F. But what is the R for gear B? It's 3 centimeters. And what's the force? Well, the force is the same between the two gears. It's 20 newtons. So the torque on B is equal to 60 newton centimeters of torque. So look what we did. Gear B is going to apply somewhere to the outside world, is going to apply 60 newton centimeters of torque. You've increased the torque. But at what cost? Let's take a look at D. What is the angular speed of the driven gear? Well, for every one time this turns around, gear B doesn't go through a whole rotation. How much of a rotation does it go through? A third. Now here's how you can remember this. The velocity of the outside of the gears are the same. Just like the forces are equal and opposite, but the velocities is in meters per second or whatever units you want to use is the same. Because these gears are moving at the same speed. And we said that speed is equal to R times the angular velocity. So R times the angular velocity for A equals R times the angular velocity for B. Okay, and so if I want to know what is the angular velocity for B, well, that's going to be RA omega A divided by RB. So this is going to be, so RA is 1 centimeter. The angular velocity of A was given to be 100 revolutions per minute, divided by RB, which is 3 centimeters. And notice that you don't have to change this to radians per second. If you actually wanted the actual velocity, you'd have to change it to radians per second, in order to multiply by the radius to get meters per second. But we don't have to do that here because these are just going to cancel out. And so it's going to be 100 divided by 3, or the angular velocity is going to be 1/3 as great, which is 33.3 RPM. You don't have to. This was probably rounded off, so we'll round this off. Sorry. Yeah, in engineering and physics, we don't deal with perfect values. We usually are dealing with estimates of measurements that are within 0.5% or 1/10 of 1% or maybe 1%. That's 3 or 4 significant figures, 2 or 3 or 4. Okay, now for part E, it says, what is the ratio of the speed? And the way I'm going to do that is the speed of A to the speed of B. The speed of A is 100 RPM. The speed of B is 33.3 RPM. Okay, thank you. Let me just move here. Which is really a 3-to-1 ratio. Okay? So we reduced the speed. It was a speed reduction 3-to-1. Now for part F, if we want to know the torque of A to the torque of B, well, what was the torque on A? Well, that was given. A was given to be 20 Newton centimeters. What was the torque on B that we ended up getting? 60 Newton centimeters. So we can cancel those out, and this is 1-to-3. Okay. So this is 1-to-3. And here's one thing I want you to notice is that these are reciprocals. If you go from A to B, if you're reducing the speed, you're increasing the torque by the same proportion. Okay? If this is 3-to-1, this is 1-to-3 in terms of speed and torque. Okay? And I've always found this stuff really confusing when they talk about, reductions or, usually you're trying to, with a motor, with a DC motor, usually a DC motor spins super fast, but it doesn't give a lot of torque. So what you do is you dramatically reduce the speed, but that dramatically increases the torque you'll get out of it. Isn't that right? Am I correct in that? Okay. So hopefully let me zoom out here, and you can see the whole thing. Okay, so this is the whole shebang here. Okay. Any questions? Okay, that is all.